Good day, folks. This is a video tutorial that I'm preparing for using the finite element calculation in 3D experience. But specific topic is the introducing imperfection for post-buckling column, Euler column. Now, there is a playlist that I've done for buckling, and I've done problems which involve post-buckling, but in order to do that, I have not used the imperfection from the linear buckling analysis to do the problem. Because at the time that I did those videos, that option was not available in the interface. You had to go to because the software, the FEA software is Abacus. You had to go and create an Abacus input file uh, after the linear buckling analysis, yeah, not input file, but it's called, I think, FILL file. And then once you put some commands in there, you have to save it and then read it into 3D experience, and then start from that point on. That's how you did the imperfection in Abacus. Now they have changed that so that it's automated in the release 2026x and probably 2025x. Uh, but that's what I'm going to be doing today. Okay. Excuse me. So here's the classical Euler buckling problem, and from uh, second year engineering course in mechanics of materials, you can find these formulas, and the buckling value, linear buckling value, is actually obtained by that formula, which is called Euler buckling formula. Now, it's about 25,000 Newton based on the data that I have. This is property, Young's modulus is the steel, property of steel. The length is 100 millimeter, 0.1 meter. The diameter is circular, and diameter 1 millimeter, diameter 10 millimeters. Yep. And here's the formula for moment of inertia. Now, I'll go quickly through these. Then, after I do the problem, I come back and review these slides. Okay. So, one of the things that you have to do is you have to do the linear buckling analysis in a case analysis that's going to be created. And once that is done, then you create create a second analysis case, and in it you as a procedure you select Rick's static Rick's step. Okay. Now, when you try to do static steps, there is some input that I have to do. Most of them are linear or the default ones. The only thing that I've changed in is the stopping criteria because there's none there, but I have done that. Stopping criteria is based on maximum deflection, roughly maximum displacement of a certain node on the top in the lateral direction. So here, and of course you have to apply reference force. The reference force is I use minus 30,000 Newton. Notice that this is not the same as the linear buckling load. This eventually, that linear buckling load that you did it in case analysis one, eventually will show up somehow. Now, yeah, let's move on. Imperfection. Once you do the linear buckling analysis, you create the second case. Then you select the initial condition and imperfection. And when you do that, this dialog box shows up, and you say, okay, why don't you select the edge from the case one, which was linear buckling, and take the first mode, and here's the multiplier factor. Okay. And you're going to run it, and you're going to get the force deflection curve. We come back and review these things. And those are with respect to the arc length. So we're going to change them with respect to each other, force versus displacement. And this is what you get. Notice that here, in this static Rick step, we did not tell the software what the linear buckling load was, but it's going to pop up here, right there. And incidentally, this goes past the 10 millimeter that is specified because probably the last step was very large. That's why it chose you to 12 millimeter. Now, if you reduce the value of the imperfection scale factor, the curve, again, that 25,000 is going to pop up somewhere in this graph, but it's kind of jacked. Okay, we're going to come back and uh, review these slides. Okay, let's go ahead to the generative shape design. Generative shape design. Yeah, I can do that in the part design too. Now, I want to create a line. Create a line. Point and direction. For the point, I'm going to create 0, 0, 0 right there. And the direction, I will use the Z direction. For the value, I have to put the length of the bar, which is 100 millimeter, right there. So this takes care of our model. Incidentally, let me change well, that's okay. You can just leave it the way it is. Now, we're going to apply material properties. So you go to Tool, Create Material, Create Material. This is going to be, you have to make sure the simulation is checked. For finite element, you need that. And then we say, okay. Okay. So it's this one. That's why I wanted to rename it, but changed my mind. Apply to this part. Let's get rid of these. Here, I'm going to put my numbers in. So double click. Okay, so we have a structural abacus. What is that? Abacus multiphysics, mechanical, elasticity. And I put down my Young's modulus, 210 GPa for steel. And Poisson ratio, I'll put down 0.3, but it's not going to be used, okay, because I'm going to be modeling this thing with beam elements. So maybe say, okay. All right, so that takes care of this. The model is made. Now we're going to go and mesh it. So go to structure model creation. Okay, MTFEM. All right. The mesh tab, beam mesh. You select this edge and put 5 millimeter size linear elements. So there's going to be 20 elements through the length. That takes care of this. The mesh has been created. Then we're going to go to properties. We want to specify the cross section. First, the beam profile. This is going to be circular, and the radius of 5 millimeter, diameter of 10 millimeter. Radius of 5. Good. Now we're going to go, this was the profile. Now we're going to go specify the beam section. So select that edge. From the beam profile, there's only one that I've created, beam profile 1. I have to select that. It's right there. And that's pretty much it. Say okay. Good. Incidentally, if in case you don't want to see the actual three-dimensional shape, there are different ways of doing it. That's what this last slide was for, actually, this one. You can do it the way I explained it, or you can actually go ahead and hide the properties from the tree, either way. Okay, good. Now, that takes care of this thing. There's nothing else to do. So now we're going to go to our mechanical scenario creation. This is where your finite element model is going to be specified with the material property and what you're going to do itself, not material property. What I mean is for boundary condition and loads and things like that. But anyway, you go to mechanical scenario creation. This is going to be case one, which is the default. That's going to be case one, right? And it's going to be linear buckling. So select, this is, let's make it structural model, finite element model that we have created. Basically the mesh and properties. So, all right, see, it's case one. Now, what we're going to do is procedure, buckle step. First case is the buckle step. And we're going to use the default here. I don't think it's going to work out, I think. Now, for boundary conditions, the select the clamp. That bottom point is clamp. This bottom point is clamp. So Euler buckling, right? And then for the, we make sure that this is turned into essentially a two-dimensional problem. So fixed displacement. So you select that edge. No displacement in X, rotation about Y and Z are fixed. That means essentially it bends in the YZ plane. Good. Now we're going to apply the load. So with load, we're going to apply concentrated load on the top. I'm showing you these slides that appeared the first few minutes. So if you, let me put the direction minus Z minus 30,000. Yeah, minus 30,000. And this thing that I'm showing you is essentially what you see over there. But this is for the rig step. However, it's the same boundary condition for. Oh, I'm sorry. No. Put the minus one. You can use minus 30,000, but make it minus one. Okay, minus one, because the load multiplier is going to come out to be the load, the Euler buckling load. You can use 30,000. It's just that the load multiplier is going to be probably 0.8 something. You multiply 30,000 by 0.8, you get your Euler buckling load. But if you put a minus one here, you get the Euler buckling load directly as a multiplier. You say, okay, good. Nothing else to do. Let me do a quick save here. You never know. All right. That's pretty much it. We're gonna run it. Notice that I've done nothing about the post-buckling step, which is the static Rex. This is just the linear buckling. In this case analysis, one was created by default. Okay, good. So we go to simulation. This is model and scenario check. Good. This is a model. This is model and scenario check. Oh, sorry. This is simulation check. Next one. This is the standard linear buckling that you see in some of the other videos in my playlist. So okay. Just that later we're going to use this in order to do the imperfection in the Rick's step. Okay. I haven't run it yet. These are just checks, simulation checks. Okay, it's a good idea to do these. So close it. It worked, and then we're going to run it. Here's the simulate, which is the running step, and it's going to be fairly quick because this linear buckling is fairly standard, and we're going to get the first 10 buckling load because that was the default modes, and we're just going to use later the first one with a certain multiplier. Yeah, it's done. Okay. These are let me close this. These are the buckling load. This is the first one. 25,000. Remember I said it's going to pop up? That's because I put a -1 there. So whatever pops up here, you multiply -1 is going to give you first buckling load. And these are the displacement, the second buckling, etc., etc. All we need is the first one. Okay, we're going to close it. Good. So then, then we're going to go and insert our second case right there. Okay, so let's go back here. We go back to scenario. Here. Go to the setup tab, scroll to the right, create analysis case. Okay, this is analysis case 2. And there is a finite element model that we're going to select. We say, okay, good. So notice that here we have structural analysis case 1, which was linear buckling, and it's done. Now we are here. So first of all, let's go and insert our procedure. Procedure is going to be static rig step. You click on it, and if I expand these two, you'll see that what I get here is exactly that. And the only thing that I'm going to change is basically the stopping criteria. There was none there. Okay, so let's go here. This make sure that this is checked. Include geometric nonlinearity, otherwise it's not going to be good. So this is already checked by default. Now, for the stopping rule, I'm going to these numbers I did not change. I keep it the way it is. You go to translation. Okay. I put the cursor there. I put the cursor to the top here and select that. So one vertex is selected. Default, I'm going to change that thing to direction 2 and the value of 10 millimeter. Okay. So now what you see is exactly what I have here. Okay. And then we say, okay. All right. So we're going to go to the initial conditions. That means you go, where is that initial condition? Yeah. Initial conditions tab. You select the imperfection. Initial condition. Here's the imperfection. It says, okay, that imperfection is coming from structural analysis case 1, which was linear buckling. The support is that line. Mode I put in, mode 1, and 0.0001. Okay, and what you see there is this. Okay, that's good. Say okay. Now notice that the boundary conditions did not propagate. Okay, so we have to do that. We can copy and paste it, but I'd rather do it again. So here I go to boundary condition, fixed. It was this line in the x direction and rotation about y and z so that it stays only in the yz plane. And for clamp, I'll select this bottom point. Clamp. For loads, I select concentrated load on the top reference load in the Z direction minus 30,000. Okay? So that is what, let me see now. Yeah, this is for the rig step. You can see that. That's what I did. All right? Everything else is the same. And say okay. And that's pretty much it. I don't think I've forgotten anything. So let me do a quick save. This imperfection is the thing that was not available when I did those that the videos in the buckling playlist. But anyway, simulation. First, model and scenario check. I don't anticipate any problem now. What you get here, is these screens that I had at first one, and then the second one, and the third one. That's what these things are. So, okay, good. And then simulation check. Basically, it says that the first one had to be run, but it was run. Okay, I'm going to override everything, so it's okay. So just say okay. Really, the first linear buckling was unnecessary because I had already run it. So it's possible not to override it, and just use the same one that I used. But anyway, I overrode any. Basically, the linear buckling is done again. That's what's happening. I'm solving both cases, which was unnecessary. For sure, this is going to be okay. And when it stops, then I say yes. I say it close and then run it. And then finally simulate. Say okay. This was the third of those things that I showed you. To see how it goes, click on the iteration tab. Now it's doing nonlinear analysis. Basically, the geometry has been modified from the initial vertical one to thousands of uh, scaled mode 1. Okay. So in a sense, yeah, everything was shifted in the y direction by 1 times 0.0001, a tenth of a millimeter. Yeah, extracting results. That's very good. Okay, couple of things. So first of all, this is rig static. Very good. And if you look at for example, displacement in this is uh, this is the slightly deformed shape. Okay. Now you can't see it because it's a thousandth or a tenth of a millimeter, and scale factor is 1. Deformation scale factor is 1. If I had used, for example, 10%, you would have seen that this initial one would actually be way further to the right. We'll see that. Now, this is going to be the initial one, this is going to be the first one. You can see that. Uh, so this is what's happening to this beam. Okay. Now, let me close that. Right. Now I'm going to go to create 2D plots. 2D plots. See that? 2D plot from the field. XY from the field. So what I'm showing you now is this, okay? So what I'm going to say is select this point, go and select this top point, top point, top point. Notice that it's picked something right there. Okay, and you can see what the coordinates of it incidentally. It's this, and the reason it's not, the reason it's this thing is, let me cancel that for a second. Yeah, that's okay. So, now, not all frames. I want all frames in a step, rig step, translation of that thing in the direction direction Y. Okay. So say okay. So this gives it a plot. So, but then notice that this is as a function of arc length. Displacement as a function of arc length. Close it. Do another one. Select select the bottom point, the very bottom point. Pick it up. And if you check the, for example, check the coordinates, you see that it's 0, 0, 0, because it didn't move. Not all frames, all frames in step, rig step. Not translation. I want the reaction force. And let's say the magnitude, we take the magnitude. We say, okay, there we are. This is force as a function of arc length. But I want force as a function of displacement. So what I'm going to do is I will go to XY plot from expression. All right. So make sure you click on f of x. This is important. Very awkward, but it's important. Combine. These are all coming from Abacus program, and this is not really nice. Some of these features are very awkward unless you dig into it, and you're not going to find a lot of information in the help. So first one is displacement. Second one is the reaction force. Notice that the units automatically change, and we say, okay, there we are. This plot, force versus deflection, is, where is it? That plot. And notice that I didn't say anything about the first order buckling load being 25,000. I put a reference load of 30, whatever, 30,000. And eventually you can see that the buckling load of 25,000 is going to come up. Now, let me show you what happens if you change the imperfection. Now, I stopped after 10 millimeter. You can let this thing going on and on and on and on, and you get the post-buckling behavior. This is the post-buckling behavior, but you don't want to stop at 10 millimeter. You want to go, you want to go up to a point you get the full deflection load. In fact, if you did it, it will go like this. Let me use my cursor. It'll go up here, you go to the right, all the way, and then it goes up again. That's how post-buckling behavior for this beam will behave. Now, let me close this. I'm going to go and change my imperfection to drop down 1, 0. Okay. See, right now, for 0 imperfection, okay, for 0, let me go back here for a second. Result, I'll show you something. Go back here. For 0 imperfection, this is a bifurcation problem. Another 0 imperfection goes to 25,000 and then horizontally. The smaller the imperfection, the closer it's going to be to that jump. But if you increase the imperfection, it's going to become more gradual. So let's go back to here to initial imperfection. And instead of this, I make it power 0, power 3 there. I drop down 1, 0. We say okay. And now we're going to go run it and look at the same plot. That 25,000 is going to pop up again, but it's a lot more gradual to the right. If it was no imperfection, fully perfect, then it just goes straight up, in theory at least, straight up, and then horizontal. 25,500, whatever. As I said, this is not rocket science, except that this imperfection thing was not available when I did these in 3D Experience, when I did these a couple of years ago. And now it's there. It's very convenient, actually. You can include other modes, mode 2 with this multiplier, mode 3 with this multiplier, and then say OK. Now let me go ahead and look at my graph. We go down here, double click, say OK. All right. If it gives you a hard time, what you do is look at the first one. Somehow this is lost. Okay, no problem. I'm really sorry. So here I'm gonna do, these are all correct, but the point, it wants the point. So I'm gonna select this. Say okay. I don't know why this happens. Go to the second one. Say okay. Select the bottom one. It's already done. Okay, and then I don't want these two. I don't want these two. So deactivate. Just forget the last one. There. So this is not as smooth as that. And you expect that because there is less imperfection here, or actually more imperfection here. All right, folks, I want to do one more thing. And that is if you go here, and let me close this. Go to the arc length. Go to not the arc length, static Rex. For stopping, let's make this thing, I don't know, maybe 100 millimeter. Okay. And then I'm going to run it. Let's see what's going on. If it goes for too long, I'm going to stop the recording of the video, and when it finishes, I come back. But let's see. You can see that it's going further than 10 millimeter. I want to see if I capture that movement upward that I mentioned. You go up horizontally and then up. Incidentally, I can stop this. Oh, it says analysis phase failed due to error. That's okay. We'll see how far it took us. It's okay. Wait until it stops. Okay, close it. All right. You have to, because it didn't run completely, you have to go ask for result. It says the results are not complete. That's okay. And then let's go ahead and I notice that if you go further down here, this actually goes, it is going crazy. But let's see if we can plot Go something different. There. For some reason, it doesn't update these things, so cancel that. Let me go to the first one. Okay. Let me cancel that. I'm going to go back to my first, my first one. It's easier to pick the points there. Double click on this. It says lost the result, so that's okay. Good, good. Let's do the second one. Good. And let's do the last one. I don't want, let's do the last one. Good. And I don't want these two. So deactivate them. Deactivate. So what happens is that, look, if you look at this thing closely, it goes up and stops around 25,000. You can see that, it's around 25,000. And then it goes and then bends up. Okay, bends up. So I told you that it goes up, horizontal, and up. But by stopping at 10 millimeter, you're not going to see it. This is the buckling one, around 25, 26,000. Okay. All right, folks. So that's it. Have fun with it.